Assalamu alaikum warahmatullah. Welcome to Chemistry Online with Mr. Ahmed Sulaiman. Today we are going to start the summary of Chapter 3 Scientific Measurement. What is meant by measurement? We are using measurements in chemistry like in physics, like in math. What is meant by measurement? A measurement is a quantity that has both numbers and units. Number and unit is a must to represent a measurement. Number and unit. As you know, when you are talking about height, for example, you are saying 66 inches. If you are talking about age, you are saying 15 only? No, but 15 years, and so on. The temperature 37 degrees Celsius. So you need to represent measurements by using number and unit. Second, what method we can represent numbers? You know, in science in general, we have very large numbers or very small numbers. To represent the numbers, you can use something called scientific notation. What is the scientific notation? Look at this number. If you have like a single gram of hydrogen, for example, contains approximately 602 and a lot of zeros beside it, how can we deal with this very large number? It's difficult. For this reason, we are using something called scientific notation. It can work more easily for the very large numbers and very small numbers as well. How can we use it? Look, scientific notation, it gives you the number written as something called the product, okay, of the number. This product of this number must be coefficient and 10 power something raised to the power of something. Coefficient and 10 to the power of something. Let's try this number we got in the last slide. How can we present this? First, you have to write the number in the scientific notation by putting decimal. It ranged between 1 and 10. For example, this number, you have to make decimal here. Look, 6.02. Then times 10 power of, and you have to count the places or digits beside the decimal. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. After decimal. So 10 power of 23. The coefficient, this is a coefficient, okay, is the number 6.02, and the 10 power of 23 is the exponent, 23. You have to make the number, as I said, greater than or equal to 1 and less than 10, or can say between 1 and 10. يعني must be the number 3, 6, 4, whatever, point something, and so on. Okay, 3 point something, and so on. Sometimes the exponent is positive, sometimes it's negative. The exponent, 10 power of something negative or 10 power of something positive. If the exponent is positive, that means it means how many times the coefficient multiplied by, or it means the large number. Positive exponent means large number. The coefficient must be multiplied by 10. In the case of negative exponent, indicates the small number, and at this moment the coefficient must be divided by 10. Divided by 10. I think you know that in math. When you write like this number, 6300000, you can move the first. You have to imagine the decimal. If the whole number like this, for example, مثلا 6913, like this. Where is the decimal here? If you have a whole number like this, imagine decimal here, because you don't have anything after the decimal. So like this number, if you have like this whole number, imagine decimal here. And look, you are moving how many steps? 1, 2, 3, 4, 5, 6. To make the decimal here, to make the coefficient between 1 and 10. So must be the decimal here. 6.3 times how many steps? 1, 2, 3, 4, 5, 6. So 10 power of 6. If the number is like this, okay, 94700, imagine the decimal here and move 1, 2, 3, 4. So it's 10 power of 4. 9.47 times 10 power of 4. This is a scientific notation for this number. As I said, some numbers have the exponent with negative, not positive. It means it's very small number, and at this moment you are moving the decimal in the right hand side, not the left hand side as we did before. Look, if the decimal here, and you have to move to make the number between 1 and 10, so you have to move how many steps? 1, 2, 3, 4, 5, 6. Now you have 6 steps, 10 power of 6, but negative 6. Why? Because you moved in the right hand side. Also, you stopped at this point to make the 8 between 1 and 10. So the scientific notation here, 8 times 10 power of negative 6. Let's try this example. If you have like this number, this decimal will move from here 1, 2, 3, 4, 5 steps. Okay? No, it's wrong. Why? Because we have to make the number between 1 and 10. So you have to make the decimal here. It means we have to move 1, 2, 3 only. 3 steps only. It means it's 10 power of negative 3. Why it's negative? Because we moved in the right hand side. And the number here is 7.36 to make the coefficient between 1 and 10. If you have this scientific notation and you need to make a process of addition or subtraction, I know you said that like this, it's easy for you in math, but I want to revise it with you. You have like this scientific notation plus this scientific notation. You know, we took the numbers repeated as common. In math, you are talking about that. Okay, here, what's the number is repeated? This exponent, 10 power of something, 10 power 3. Take it as common and make addition between this number and this number. Look, 5.4 plus 0.8 or 0.80 times 10 power 3. Finish this first, you will find it 6.2 times 10 power 3 as it is. If you want to addition. If you want to make subtraction, the same process. Let's move to another thing. We have something called accuracy, precision, and error. What's the difference among them? Let's see. First, what meant by accuracy and precision? In chemistry, we are dealing with numbers, and each number has its own meaning. So you have to be accurate in your numbers. Accuracy means if you have a measure, how close this measure or measurement to the actual or true value. How close to the actual or true value. But precision is a measure of how close this measurement to one another. How come? It means if you have boiling point of water, it's measured by scientists and it's 100 degrees Celsius. This is the boiling point of water, 100 degrees Celsius, boiling point of water. If you are making an experiment in the lab and you are making measurement for, or you want to measure the boiling point of water in the lab by thermometer, for example, يعني something simple, okay? And you put this boiled water and thermometer, and the thermometer is, for example, 92.9. Then you repeat it again, the experiment, and you find it 99.8. Then you repeated it and you find it 99.99, and so on. Here 90, for example. Here 90 مثلا. Okay? All of them are very close to each other, yes, and also very close to the true number. If the value is close to the true number, the actual number, it means it's a accuracy measurement. If it's close to each other, it means it has precision, this measurement. طيب, what if you measure the boiling point of water and you found it 97, for example, degrees Celsius? Then you repeat it again and you find it 97.1. You repeat it again, you find it 97.3. Then 96.9. All of them are close to each other, yes, but they are not close to the true value. It means these values have precision. They are close to one another, yes, but not accuracy. Why? Because they are not close to the true value. طب, what if you measure the boiling point of water and you found it 99.98, okay, and you repeat it again and you found it 97.1. At this moment, the readings called what, or they have what? The first one is very close to the true or actual value. It means the first one has accuracy, yes, but both of them are not precision. Why? Because they are not close to each other, not close, 99 and 97. So they are poor precision. They have poor precision. But first one has good accuracy. You understand? I think you understand. It's easy, and you'll understand more if you see that. To evaluate the accuracy of the measurement, you have to compare this value to the correct value. At this moment, it has accuracy, or you can say accuracy or good accuracy. But to evaluate the precision measurement, you have to compare this value to one another, if it's repeated or not. Look at this diagram and you will see the meaning here in this diagram. Look, if you point to this point and all of the arrows are in the same point, which is the correct or true point, we can say, because all of them are at the correct point, so they have good accuracy. They are very close to the true value. Also, they are close to each other, so they have good precision. But what if they are close to each other? Yes, they have good precision, but not close to the true value. So we can say poor accuracy. Good precision, but poor accuracy. But what if they are farther from each other? That means the poor precision, and also far from the true value. So at this moment, poor accuracy as well. You got that? So we got the meaning of accuracy and precision. Now we need to determine the error. What is the error? If you are measuring the boiling point of water, as I said, by thermometer, and the thermometer reads 99.1 degrees Celsius, not 100, you accept this value. Must be 100 degrees Celsius. This is the actual degree, but we have the reading 99.1. From these two readings, the actual one you know, and the measured one, you measured it by thermometer, you can find something called the error. How? You have something called accepted value, which is the correct value, which is and you have something called experimental value that you measured in the experiment. If you want to measure the error, just make the subtraction between experimental value and the accepted one. Let's try this example here. Look, we have the true value, which is 100, and we have 99.1, which is measured one. 99.1 minus 100, it gives you negative 0.9 degrees Celsius, because we make subtraction between the experimental one and the accepted one. The experimental one, which is happened in the experiment, 99.1. The accepted one, which is accepted by scientists, measured by scientists, which is 100 degrees Celsius. Make subtraction between them, you will find it's negative 0.9. If you want to measure the percent error, just put the error here, okay, but the absolute value of the error, without negative, I mean, okay, divided by the accepted one, okay, not the experimental one, the accepted one, measured by scientists, times 100%, you'll find the percent of the error if you need the error in the form of percentage. Let's see this. You have boiling point 100, but you measured by 99.1. We need to calculate the percent error at this moment. How? Look. This is the rule, the absolute value of the error divided by the accepted value times 100%. Look, 99.1 minus 100, which is negative 0.9, but without negative because we need the absolute value, so it's 0.1, divided by the accepted value, which is 100%. It gives 0.9%. This is the percent of the error in this problem. Let's move to something else. We have something called significant figure. What is a significant figure? In the temperature, in anything, you can represent the numbers to the nearest degree or nearest value. Like this value. You have, for example, you estimate the temperature between 22 and 23 if the temperature is 22.9. So it's between 22 and 23. To identify the significant, and how can we say the significant figure at this moment? 22.9 degrees Celsius estimated in 3 digits. 1, 2, 3. 3 digits. The first 2 digits, which is 22, 2 and 2, it's known as a certain. We call it certain value. While the rightmost digit, which is a number after the decimal, 9, has been estimated and involved uncertainty. Not certain, and you are not sure about that. To identify the significant figure, you have to identify how many digits you have to represent the numbers by. So the significant figures in the measurement include all the digits, not all of them in general, all of them that are known, plus last digit that is estimated. So all of them that are known and also the estimated ones. We don't understand 100%. We need to find some examples to understand more. let's determine the significant figure for some measurements. But we have rules. You have to know the rules to identify the how many significant figures you have in this number, in any number. The first rule, rule number 1, if you have non-zero digits, it's reported as a significant at this moment. Like these examples, you have here two numbers here before the decimal and after the decimal 1, and all of them it's non-zero digits, no zero here, okay, and all of them are significant because we can measure them or we can identify them, so we have 3 significants here. What about here? We have 3 as well. 1, 2, 3. What about this 0? No, it's 0 in the left hand side. We cannot put it as a digit. Look, 1, 2, 3 here as well. So it's 3 digits or 3 significant figures as well. If you have 0 at this moment, what happens? If there is rule 2, if you have 0, repeating 0, between non-zero digits, this is non-zero, it's not 0, this is not 0, but between them, zeros. We count them? Yes, we count them. At this moment, how many significant figures in this number? 4. 1, 2, 3, 4. What about this 0 between non-zero digits? Yes, counted. 1, 2, 3, 4. Here, 0 between non-zero digits, counted. 1, 2, 3, and 4. This is rule 2. Rule 3, leftmost 0 appeared here in front of non-zero digits. Counted or not? No, not significant at this moment. How come? Look, you have zeros here, but not between non-zero values. Okay, so we count only those 1 and 2. So we have 2 significants here, significant figures. What about this 1 and 2? We don't count this 0. Look, 1 and 2. We don't count all of these zeros. Why? Because they are not zeros. They are not located between non-zero values or numbers. If we represent any of these numbers by scientific notation, we count the values here by 2 significant figures as well. 2 significant figures as well. 2 significant figures as well. We are talking about coefficient here. What about the exponent? We don't count them at all. This is rule 3. Rule 4. If 0 at the end of number in the right hand side, not left hand side, this decimal at this moment make these zeros counted or not? Yes, they counted. Look, like this example. If you have 43 meters, but we have decimal and 0, 0, we counted them. Why? Because they have value, the digits have value here, even they are zeros. Look, 1, 2, 3, 4. What about this? 1, 2, 3, 4. Zeros between non-zero values counted, and 0 in the right hand side counted as well according to this rule, so they are 4. What about this? 1, 2, 3, 4 significant figure as well, because they are in the right hand side of the non-zero value. We can find significant figure here by these rules, and first rule, all non-zero digits like 1, 2, 3, 4 up to 9 are significant figure. Okay, if you have like this number 1, 2, 3, 4, 5 significant figures like this. Okay, rule 1. Rule 2, if you have zeros, if the 0 is to the right of the number, we have two cases. If the number is decimal point like this, we count the zeros. Look, 1, 2, 3, 4. The decimal here and the zeros are in the right hand side. What if the number without zero but like this, 1, 2, 3? If zeros are located in the after the zero, after decimal, in the right hand side with number, we count all of them, 1, 2, 3, 4, 5 significant figure. This is the first case of zeros, right to the number. What if the number without decimal, no decimals? We count only the number, not the zeros. Look, this is one significant figure only. This is two significant figures only. This is two only significant figures. Different from this case, okay? Because here, no decimals. طيب, this is the first case of rule 2. Second case of rule 2. If the zeros in between digits, we count them? Yes, we count them. Look, 0 here, we count them. 1, 2, 3, 4. Zeros here, so count them. 1, 2, 3, 4. 0 here, even decimal found or not, count all of them, but only the 0 in the left hand side don't count this 0. We count only those 1, 2, 3, 4, 5, but we don't count 0 outside the number which is in the left hand side. The third case of zeros, if the 0 here in the left hand side with decimal or without decimal, we don't count them. Look, here two significant figure only, we don't count them. Here one significant figure only, we don't count this, even with a decimal here. Here two significant figure, even we have decimal, we don't count these three zeros, so we have two significant figure here. Trailing zero or special cases. If you have like this value, it means it's about 80 centimeter, about 1,300 kilometer. Okay, we don't count this zero at this moment because special case for zeros. Okay, so we have only here one significant figure, here two significant figures only. Type. What if the like this count zero or not? If the whole number here without decimal point and like the previous one, but preceded by word precisely, accurately, at this moment we count them, these zeros. Look here, it's just like approximate, we don't count this zero, but if it's accurately, we count them. Look, 80 centimeter, yes, we have two significant figure here, 1,300 kilometer, okay, precisely, so we have four significant figure at this moment. Let's try these examples very quickly. Look, we have this value. How many significant figure here? 1, 2, 3, 4. Counted all of them. What about this number B? We have zeros, but between non-zero values, so we count them. 4 significant figure. Here 3 only. 1, 2, 3 only. Why? This 0 not counted. Okay, not significant figure. Here only 2 because we don't count these two zeros. Here 4. Why? Because we have decimal here, so we count all of them here. 4 significant figure. What about this? 34,000. Only 2 significant figure because we don't count these zeros. No decimal here. What about this? We have 1, 2, 3, 4 only because we don't have decimal and we cancelled all of these zeros not counted. Okay, so we have 4 significant figures here. What about this? 1, 2, 3, 4, 5. We count all of them because we have decimal point here. What about this? 1, 2, 3 only. Why? Because no significant figure more than this, because we have these numbers in the left hand side. What about this? 2 significant figure. Why? Because specific. Okay. What about this? 1, 2 normal, because we have decimal. What about this? 1, 2, 3, 4, because we have the right two zeros, look, are significant. The right two zeros. Right two zeros are significant, so we count them, but the left hand side we don't count them. So we have 4 significant figure here. What about the next? 2.40 centimeter. We count all of them. The 3 are significant. What about this? 1, 2, 3, 4, because we have decimal here, so we count all of them, and this 0 is the left in the right hand side, not the left. What about this? 1, 2, 3, 4, 5, 6. We count all of them. We have decimal, so we count all of them. What about this? Only 1. Why? Although we have decimal, because all of these zeros are in the left hand side. What about this? 1, 2, 3. We don't count this exponent, as I said. So 1, 2, 3, 3 significant here. What about this? 1, 2. We count this 0 because it's in the right hand side, and also we have decimal. Okay, so 2 significant figure here. What about this? Only 1. What about this? 1, 2, 3, 4. We count this 0 in the right hand side, and also we have decimal. So we have 4 significant figure in this case. I think these examples are very clear for you and good training for practicing. You have some other practicing. Check your understanding here for these numbers. How many significant figure here? 1, 2, 3, 4, because we have decimal. The number here, how many? 1, 2 only, although we have decimal, but they are in the left hand side. The number of decimal places here is 3. Okay, decimal places means how many places for decimal? 1, 2, 3, something else, not significant figure. It's something called decimal places. Okay, 3 decimal places. We have 3 places after the decimal point, it means. What if we have multiplication and division of numbers? How can we deal with a significant figure? In the calculation of multiplication and division, you need to round the answer to the same number of significant figure, but the least one, the least number. How come? Let's see this example. Perform the following operation and answer the question. Look, we have 7.55 meters times 0.34 meters. Also 2.10 meters times 0.70 meters, 2.4526 meters squared divided by 8.4 meters, and 0.365 meters squared divided by 0.0200 meter. How can we deal with these problems? Let's try the first one. How many significant figure here? 3. How many here? 2. The least one is, which is the least one? 2. So the answer must be 2 significant figure, not 3. That's it. How come? Look, the process is the answer is 2.567 meters. So you have to write it in 2 figures only, 2 significant figures only. 2 point and make round. 5, make it instead 5 if this is less than 5. Still 5 here. But if it's more than 5, so make it 6. So change it to 6. So it's 2.6 at this moment, and we make it 2 significant figure only, the answer. To understand more, let's try the second example. 2.10 have how many significant figure? 1, 2, 3. How many here? 1, 2 only. So the answer must be 2 significant figure only. Let's try. Make the process or multiplication, and you'll find the answer is like this. Here 3 significant, but must be 2. So make round. Round the 4 into 5 because beside it 7. Now 1.5 is the answer. Let's try the third one. We have how many significant figure here? 1, 2, 3, 4, 5. We have 5 significant figure, but the second one has 2 only significant figure. So the answer must be 2 only. How come? Make the division. You will find this value. You have to make round to make them 2 only. Round this 9, still 9 because beside it 1. So it's 0.29. And at this moment it has 2 significant figure only. The last one, how many significant figure here? 1, 2, 3. Here 1, 2, 3 because we don't count the left hand side. Both have 3, so the answer must be 3 because no one of them is less than the other. Okay, so the answer must be 3, but the process gives me 4 digits here. We have to change it into 3 or round it into the form of 3 significant figure only. So round these 2 into 3 because beside it 5. So 18.3 is the correct answer for this problem. Significant figure is an operation, and as I said, you can round the values to the least significant figure of the numbers in the process. Okay, I said that. I said all of that. Also, if you are making addition or subtraction, not multiplication and division, if you are making addition and subtraction, the final result must be no more accurate than the least accurate number as well. Like this. If you have like these values, okay, we have here something plus something. How many significant figure here? 1, 2, 3, 4. And here 1, 2 only. Okay, so the answer must be 2. The result of the addition here must be 2, the least one as well. Okay, the least one. The result is 9.311 centimeter. Round it into the form of 2 decimal places only. Not significant figure at this moment. It's called decimal places. Decimal places. It means we need to make the least number of decimal places for the result. It means must be 2 decimal places only. 2 digits after decimal. It means. So the answer must be 3, 1 only, and we have to cancel this one or round it into 1 because beside it 1. So like this. Not significant figure ya shabab. It's decimal places. Decimal places means rounding the answer of addition and subtraction to the least number of decimal places in the process. The least number of decimal places in the process. We have here 2 decimal places. The answer must have 2 decimal places only, the least one of the process. Not significant figure here in the case of addition and subtraction. Look at this. How many decimal places here? Sorry, this is multiplication. So significant figure. How many significant figure here? 1, 2, 3, and here 2. So the answer must be 2. Which one of these? This is 2. Not this. This is 3. This is 4. This is 5. So the true answer, correct answer is this. What about if you have like this example? If you want to make difference, subtraction between D equal A minus B. A is this value and B is this value. So this minus this. How many decimals here? 1. How many decimal places here? 2. The answer must be or must have only 1 decimal place. Which one here have decimal places 1, this is 2, this is 2, this is 3, this is 1. This is the correct answer. You understand? So counting significant figure and decimal place is easy now. You can count the significant figure in the measurement by this process, and we have many examples here. Look, according to the rules, how many significant figure here? 3, according to rule 1. What about this? How many? 1, 2, 3, 4, 5. What about this? How many? 5. 1, 2, 3, 4, 5. All of them are counted. What about this? 22. Unlimited significant figure here, as you said. What about this? 1, 2, 3, 4 only, because those are in the left hand side, not counted. What about this? We have 2 only, because those are not counted, because we have no decimal point here. SI units. What's meant by SI units? It's like System International or International System for Units. It's like French system. You studied before that. I just remind you. Okay. And we have 7 cases of quantities have SI base unit, and each one has its symbol. For length, meter; for mass, kilogram; for temperature, Kelvin, not Celsius; for time, second; for amount of substance, mole; for luminous intensity, candela; and for electric current, ampere. They are 7. Each one has its own symbol. You saw them before, I know, but just remind you that. And we have for each one some prefixes we are using in the number. For example, if you have not gram but megagram, or byte, megabyte, or whatever. Mega, what does it mean? Means 1 million or 10 power of 6. You have to remember this. Kilo, its symbol is K, and it's 10 power 3. DC, decimeter, decigram, DC something, it means 10 power of negative 1 of this. Centi means 10 power of negative 2. And milli, M small, means 10 power of negative 3. Micro, its symbol is mu, like this symbol, and it's 10 power of negative 6. Nano, N small, and it means billion times smaller, or 10 power of negative 9. Pico, B, and it's a trillion times smaller than the unit, and it's a 10 power of negative 12. Some prefixes needed in our calculation, like this. This for lengths. What about for volume? We have something called liter, L capital; milliliter, M small, L capital; cubic centimeter, cm power 3; and microliter, mu and L capital. These are symbols for volume, and each one has the rule for conversion. Quart of milk equal 1 liter. If it's 20 drops of water, it means 1 milliliter. If it's a cube of sugar, means 1 cubic centimeter. If it's a crystal of table salt, it means 1 microliter. These some examples of units of volume, units of mass, which is important. Kilogram, okay, the basic unit, which is 1 kilogram equal 10 power 3 grams, or 1000 grams. Gram, G small, 1 gram equal 10 power of negative 3 kilogram, because gram is smaller than kilogram, طبعا. Milligram, mg, which is 1000 of gram, and each gram has 1000 of milligram. And microgram, which is 10 power of 6 microgram equal 1 gram. 1 gram equal 10 power of 6 microgram, something very small. This is the units of mass. And we have other units of quantities we are using in chemistry, like energy. Units of energy is joule, J, Okay, this is the name of a scientist. And other units for energy like calories, calorie, CAL, by small letter. And if it's by capital letter, calorie, it means 1000 calories from small letter. Okay, you have to remember this. Okay, and if you want to convert el joule into calorie, 1 joule equal 0.2390 calorie with small letter calorie, or the opposite. If you have 1 calorie, it means equal 4.184, or you can say 18 joule. If you want to convert calorie to joule, just make multiplication. I'll give you an example very quickly. If you have 3.4 calories and you want to make them in joules, calorie to joule, just multiply this value by 4.18 or 4.184. It gives you the value by joule. If you want to make the opposite, if you want to convert joule to calorie, okay, and you have, for example, 7.3 joule, just multiply this value by this 0.239 times 0.2390 equal value by calorie at this moment. You change the joule into calorie, so it's easy to change one unit to another. I think it's easy to change joule to kilojoule, or kilojoule to joule, because kilojoule equal 1000 joule. Kilo is easy for you. This is the end of summary of chapter 3. I hope to understand everything in this chapter. Thank you, Shabab.